Okay, this is the moment you've all been waiting for. We are going to find the exact area under this curve. And so let's start with what we know. We know that we can approximate the exact area under the curve using rectangles. And we also know that the more rectangles we use, the more accurate that approximation becomes. And so we've talked about this a little bit in class. What's the ultimate number of rectangles to use? Well, in this, it's 100, but really it could be 200, 300, 400, all the way up to 1,000,000. Infinitely many rectangles is what we want. So we're going to take that concept and run with it here. So stay tuned. Okay, so this is going to get a little abstract, but just stay with me here. When I have these sub-intervals for the width of my rectangles, let's just call this x sub 1, x sub 2, x sub 3. This will be x sub 4. I guess down here we could say x naught. And we're going to go ahead and draw these rectangles in. Now, I ended up using a right-hand Riemann sum to do this, and I used 4 rectangles, which we know is not going to be a very good estimate. But keep in mind that I can say that this area, a sub 4, I'm going to use a for area, can be the height of the first rectangle, so that's going to be f of x sub 1, times the width of the rectangle. And the width of the rectangle is going to be x sub 1 minus x sub 0, or as we say, x naught. I'm going to add to that f of x sub 2, that's the height of the second rectangle, times the width, x2 minus x1, plus f of x sub 3 of x3 minus x2. And I just keep this going for 4 rectangles. x4 minus x3. Now, a more general way to write this, because that's a pain to have to write this out, especially if I have 5, 6, or 7 rectangles. I can use, let's go back to your days of pre-calculus, I can use summation notation. But I'm going to let I represent an arbitrary variable here. So I'm going to say x sub I instead of x sub 1, x sub 2, x sub 3, x sub 4. I'm going to say x sub I, and I'm going to let I, in this case, go from 1 to 4. And so I can say that it's the height of the rectangle, f of x sub I, times the width of the rectangle, which is going to be x sub I minus, well, the one that comes before that. And that's going to be x sub I minus 1. Okay? Even more generally, I can say that this is the summation from I equals 1 to 4 of f of x sub I times delta x sub I. And delta is the change in x. All right, now, we know that 4 rectangles is not enough. How many is enough? Well, infinitely many is enough. So let's just start with n number of rectangles, right? I can have any number of rectangles I want. So let's say n number of rectangles. So I'm going to come down over here. I'm going to write this in a different color. And we're going to say if I have n number of rectangles, then a sub n, the area of n rectangles, is going to be the sum from I equals 1 to n, right? Because I have n number. If I had 4 rectangles, it would be 1 to 4. But now I have n rectangles. And it's going to be f of x sub I, that's the height of each rectangle, times delta x sub I. All right, so that's n number of rectangles. Now, what's the ideal number of rectangles? Well, the ideal number of rectangles would be infinitely many. So what we can say is that the area under the curve is going to be, if we want to let n go to infinity, we're going to use limits. We're going to take the limit as n goes to infinity, the limit as n goes to infinity, of the summation of I equals 1 to n of f of x sub I times delta x sub I. And this right here, area, is going to give me not just an approximation of the area, but because I'm letting n go to infinity, it's going to give me the exact area underneath this curve. And that is kind of a cool concept.